because I hammered that one.
I nailed mine too.
Welcome to the Hackaday podcast. I'm Elliot Williams, editor-in-chief of Hackaday.
And I'm Dan Maloney. I'm a staff writer at Hackaday.com and community engineer at Hackaday.io.
This is episode 168, Math Flattens Spheres, FPGAs emulate arcades, and we can't shake Polaroid pictures. This week in the news, we've got no news. What the heck?
No news is good news.
Tell you what, but that means we can go straight into What's That Sound?
This is a journey into sound.
What's that sound?
What's that sound?
So if you're new to What's That Sound, I play a sound and you try to guess what it is. You head on over to hackaday.com/podcast. You fill out a form with your guess and your handle that you want to be called on the air and your email address. And then the next week, if you guessed it right, and if the random gods are kind to you, I'll shoot you an email, get you a Hackaday t-shirt. You ready to hear the sample this week, Dan?
Sure am. Let's go. Weird. I don't know. Something with a modem. It's modulated something. I'm not exactly sure what the modulation is.
Fair enough. It's modulated something. You guys out there, tell us what that is, and you stand a chance to win a Hackaday podcast t-shirt. I won't give you any clues.
Okay, fair enough.
So off we go to talk about hacks. My first hack this week is from Mr. Retro Wolf, and the title of the article is Will Mr. Fool You Into Learning FPGAs? And Mr. FPGA is a project to clone was a project to clone the Atari ST on an FPGA completely and entirely. So you could just run Atari ST things on it. It did that successfully and has since then grown to clone all sorts of other retro computer systems, including C64, etc., etc. The Mr. FPGA is an FPGA dev board, completely open source, that includes all the things you might need to emulate a retro computer, so like joystick ports and a place to plug your VGA in. In this video series, Mr. Retro Wolf is developing a video game from scratch, or I guess I should say he's cloning an old arcade game from scratch as a learn everything you possibly could about developing on FPGAs while simultaneously reverse engineering an old arcade game console. It's a fantastic video series. I think he's up to 13 now, and they're all about half an hour long, so I've just dipped in and out of a whole bunch of them. He's about 2/3 of the way there, I would guess, by now. If you're at all interested in learning how either old arcade games worked or how FPGAs work, this is a great series to follow along with. He picked Tank Battalion because it's a really simple game and because nobody had an emulator for it yet, and because he could get his hands on both the schematics from an arcade machine repair manual and also on the ROMs from MAME emulations of it. So he actually has everything he needs here to make a Tank Battalion game, first of all, on a breadboard. And so he takes a 6502 processor chip and all of this support logic, and he builds out the entire logic of the main board of this arcade game out on a breadboard. The rest of this video series is him then kind of turning this all into Verilog code to implement exactly the same device, like gate for gate, in the FPGA. And it's a little bit heavy at times, but it really clarifies a lot of things about, I watched the tile map system video in its entirety, and it's just a fantastic explanation of how tile maps used to work in these old school computers and arcade machines, and then how it's implemented in logic chips, and then how those translate into the FPGA fabric is just fantastic to watch from beginning to end.
Yeah, something about these FPGA emulation, retro computer projects that I just have to say leaves me feeling flat.
Okay.
I I don't know what it is, but let me just preempt the comments on this. This one kind of changes that a little bit because of that breadboard filled with 6502 and supporting chips and all that stuff. Realizing that as gateware, as you said in the article, inside the FPGA kind of salvages it for me a little bit. I don't I don't want to sound snooty or anything like that. I don't know. I don't know how to put it, but to have a box with what essentially amounts to a single chip and having that do the business of what guys like Bill Hurd, took hundreds of chips to get done.
Yeah.
And
totally
slavishly optimizing the design and, getting rid of a chip here and a chip there. And, we can use, a NAND gate as an inverter here and all this optimization stuff, manually routing traces, things like that. All that stuff really speaks to me. And the FPGA projects kind of get around that in some ways. But I understand them because I think someone said in the comments that what's your choice right now? If you want to have these things, there's kind of no way to do them in actual silicon. The real hardware is getting harder and harder to find. And a project like this is clearly the, quote unquote gateway drug to FPGA design. This is something that you can sink your teeth into as a project, because it's coming up with something tangible and something that that you've already seen before. How it's going to act. All those things are there to make it easier for you to figure out how to use FPGAs for later projects where you don't know how you want it to come out. So I see the utility of these projects, and I appreciate them, and I especially appreciate build like this, which goes from breadboard to FPGA like that is really stunning, and the tools that it provides you with are really valuable. And I guess it's just a long-winded way of saying I don't take your FPGAs and get off my lawn. I don't get it yet.
That's what a lot of people in the comments said. I mean, a lot of people are like, I don't know why you'd want to use an FPGA when you could just use an MCU. And that's probably right for a large series of problems. Like, there's probably a huge classification of problems for which you should just be using a CPU-based design and, move along then. And a lot of people, I think, thought of this as being a means to an end, that is, a way to get an arcade emulator. And I'm not sure it is. I think the whole point of Mr. FPGA project actually has become teaching people how to do retro computers on FPGAs. And so it's more about that than it is about getting a retro computer. Because if you really just wanted a Atari ST emulator, you fire up MAME, load up the Atari ST emulator, do this on your computer that has 27 cores and all running at 6 million gigahertz. I mean,
if you just want to play a game, there's way easier ways to do it.
But when you do want to do something that requires an FPGA, like, some kind of video stream processing or something, then you're stuck with software. Then you have a problem. Like, there you're going to throw way too big a part at it. It's going to kill your power budget. Blah, 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 blah. I mean, there's a bunch of good reasons to learn on an FPGA, but then this is not that project. This is the project to teach you how to get comfortable with them first, I think. And for that, it's really good, like you said. What's really neat about it as a starter project is it does have a CPU in it, right? It's got an emulated 6502 chip in there, among other things. It ends up being a kind of complete arcade game computer system all inside the logic. And I think that's sweet. The one-to-one correspondence between, when he's programming the ROM in there, it's really cool. But then this only goes as far as kind of 1980s tech. And the really heavy stuff in FPGAs kind of takes off after there and gets into how you do pipelining of things and how you make sequential processing out of its essentially natively parallel processing. And that's where my mind starts to bend a little bit, but it's also where the really, really cool stuff is. So, this will get your foot in the door and really, really well. I don't know. I'm enjoying watching this series. I'm going to have to catch up on a whole bunch of them and follow it from here on out. Because A, I like watching old machines get built up from scratch, and B, I like watching them get turned into Verilog. I'm weird.
We'll just accept that.
If you don't, you don't have to.
Speaking of retro computers, my first pick is a nearly all new Commodore 64. This is by Retro Shack. And I mean, this kind of brings me back because my first quote unquote real computer was a C64. I mean, I have nothing but the fondest of memories for learning computers. That was my platform for trying things out. And first time writing basic programs, first time getting online with CompuServe. Yeah, huh? You know, the BBS scene, the 300 baud modem, all that stuff. When that C64 setup foolishly went into a yard sale and went off to someone else, I probably didn't even think anything of it at the time about what the loss was there, especially since they had my discs too. I did a lot of work, a lot of word processing and stuff like that. I actually did most of my first couple of years of college on a C64.
Yeah.
But anyways, this project is about creating a new one, kind of from scratch. The PC board that they came up with here is a replica of the original PC board. It obviously has to differ in some ways from the original. Some parts just don't exist anymore. The video modulator is done completely differently from how it was done on the original board with that metal can for the RF protection and all that stuff. That's totally different. But I mean, it really is. It's all through hole parts as far as I can see. Even got the fuse sitting on the main board, which is a nice touch. It's a 6502, straight up. That's what it is. It's not an emulator. It's not there's not a Raspberry Pi sitting in there someplace to do the job. It's the 6502 and a bunch of other support chips plus all the other chips from this that made the C64 so unique. What's good about it is it's now, if you're getting to the point where even though these machines were made in the millions and there's still a lot of them around, not a lot of the ones that are around aren't either spoken for already, and so it's going to be difficult to get them if somebody already has one. But also the ones that are available, some of those components are going off, and there's a thriving YouTube community, videos that show how you're going to get this busted C64, VIC-20s, all those computers, how you're going to get them back into working shape. And those are fascinating. But if you're just looking to get your machine, get your hands on a machine and get back to work with it, basically, after 40 years or so, this might be the way that you have to go. It's not completely new stock. I believe that at least one or two of the chips has to be salvaged from old defunct boards. So if you've got an old C64 lying around, you might need to take one. I don't know what chip it was that they
Probably
said that
notoriously the SID chip.
Probably the SID chip.
Because that had an analog filter in the silicon, and it had some weird power glitches and stuff like that people abused to make sounds particularly in a particular way, because you could kind of glitch out the chip. And some of that stuff, there's just I don't know if there's a super good replica for. I know people have worked on it left, right, and center. I don't know what the state of the art is. So you probably need a SID.
Yeah, you need to salvage that from an old machine. But aside from that, if you could order up parts from DigiKey or Mouser, which seems to be a little bit of a problem these days, theoretically these chips are all available, and the design is beautiful. The design of the board is beautiful, and even unpopulated with chips and just sitting there with the sockets, it's quite something to look at. I really appreciate the amount of work that went into this, and hopefully it'll maybe bring some nostalgia back for the C64, maybe also get some people in who missed the C64 days and get them figuring out what the machine can do for them today.
Next up, this spherical lamp's pieces ship flat thanks to math. This is a sweet looking lamp design by Nervous System, which is kind of a mathy computational design lab where they make a whole bunch of really cool things. If you're into kind of computational art, you should go check out their other work too. Here, they've taken basically a three-dimensional sphere and cut it up into some particularly interesting, lovely, organic geometric shapes. and then laser cut them out of thin veneer wood. And when you assemble the thing together, it kind of reforms back into a circle and makes a lovely lampshade. But the coolest thing here for me is they have a video of how they designed this, and it's just kind of inspirational to think about how you could do this kind of design tricks in your own stuff. And in particular, what they do is they start with a sphere and they kind of do the usual soccer ball trick where you have like a bunch of hexagons and pentagons and you put them all together so they make a round shape. And then they warp all of the edges of these, and it's like they just twist them into each other. And so instead of being their original kind of regular geometric shapes, they become these insane organic shapes that nonetheless have exactly the same properties that they used to, because it's, the same thing but kind of just twisted. There's just something lovely about watching them take these flat pieces and just riveting their edges together slowly, and then what starts coming out of it is a hemisphere, and then you clip some more parts on, and it makes a ball at the end. It just looks really fantastic, and it's a great trick, and it does make me think about maybe I need to be thinking about how to make tiling three-dimensional things.
You look at it and it looks like something you see through a microscope if you're looking at a section of plant tissue or something like that. The way the cells line up and snuggle up against each other and form barriers and form structures. Very organic looking. And in that video, they do actually mention that. These are puzzle cells, which are, as the article says, complex interlocking cellular shapes. And they do show that in nature, in a leaf. You can see the almost identical pattern is showing up in nature. So it's kind of cool that they're finding the math that nature uses to solve a huge set of problems and building something beautiful out of it. It's kind of a cool look, and I love the way that it brings the math into a concrete sort of realization.
Actually, now that I look at the comments, since I last looked at this article, Jessica from Nervous System came in the comments. Somebody said, so this is modeled in Rhino or Grasshopper, and she says, nope, custom C++ code. You can read about it. The flattening method is based on a new technique from Keenan Crane's group at Carnegie Mellon. So that gives me a research paper that I'm going to have to look at.
Okay, my next pick is All the Sticky Labels You Could Ever Need, No DRM, Just Masking Tape by Jenny List. This one is a project by Michi Martini, and it's really, really simple. I mean, we all know that there's problems with label makers these days. There's been a lot of news about how Dymo, one of the big label printer companies, is now putting some sort of RFID chip or something like that in their label stock reels, and you can only use their labels, and guess what? They're real expensive. This one, no worries about that at all. Until they can figure out how to DRM a roll of ordinary masking tape, you should be golden with this. It's basically a pen plotter that just moves a pen over the radial axis of a roll of tape and lifts the pen up and down with a servo. It's got an old DVD drive lead screw to run it radially and a stepper motor to rotate the tape. And that combination of motions, a little Gerbil, a little G-code, and you've got yourself letters on tape with the magic marker in the pen position. It's really neat. There's a video that was embedded in the I think this was an IO project. Yeah, this was an IO project. There's a video that was embedded in there, and one of the commenters put it in the comments, so you can check it out. The printing that it does on the labels is very neat, and in fact, there's a couple of different fonts that you can choose from apparently. And obviously you can do whatever you want because you're programming it yourself. I think you even sent an SVG, a link to an SVG from the Jolly Rancher along, so that we can hopefully see that embodied in masking tape at some point soon.
It's funny you mentioned that I went in there because I was watching that video was what really sold me on this one. It's just such a beautiful mechanism. And this is kind of a second or third iteration of the design. And actually, if you go halfway through the video, Michi has a demo of an earlier version of it. And the pen's on a little bit of a slant and it's got some backlash in some motor somewhere. And it just really It does a pretty good job, but it's not amazing. Whereas this one, the pen is dead vertical, like straight down the radius, and doesn't slip sideways, and it doesn't wobble around in its little collar. And that sort of stuff makes all the difference. I guess also plus having a really nice dark black pen. I'll admit it. I was so struck by how nice a machine this was and how nice and simple a machine this was that I'm like, oh, dude, I'm going to go find myself an SVG of the Jolly Rancher and send it to this guy because he needs to be doing that. And then I went back and looked through his code, and it's based on HF2G code, which is Hershey Fonts 2G code. And so he probably can't even use my SVGs without like retooling his whole software toolchain. So I suck. The whole thing is doing it in a way that he totally can't make use of what I put up there. But the rest of you who need a good Jolly Rancher SVG file, there's one in this post. Go pull it down. That's a good one. Anyway, I just thought it was too funny. But that's actually neat in and of itself for drawing out letters like this. It's written in C and it's running on the microcontroller, so he can't make use of my Jolly Rancher SVG at all. On the other hand, Hershey fonts are fantastic, and when you want to make a label writer that doesn't have to deal with the thickness or the thinness of letters and just needs to have some readable text, this is a super resource to know about. And actually, if you want to learn something cool about the history of the Hershey fonts, Chris Lott wrote us a fantastic piece about the history of Hershey fonts and the guy who invented them and gave them to us all in the form of a book back then. Public domain, lovely piece of work that basically everyone who's ever made line art lettering has benefited from in the meantime. You should go check that piece out. I'll throw the links in the show notes.
The thing that actually got me about this was, okay, well, what happens when, you wrap around to the other side of the piece of tape? You can only go the circumference. Your message can only be the length of the circumference. So the next generation of this would probably have to have some sort of take-up reel or some way to pay it out so that you could continue using the rest of the roll. And then someone in the comments said, well, what about the shrinking diameter that's going to, as you pay off tape, it's the roll's going to get smaller. So you could continue on with this one, obviously, and do a full build out of this. But the ability to write whatever the circumference is of the roll of tape and be able to write the message is fine by me the way it is.
How much does the circumference of a roll of masking tape change as you go from full to empty? I mean, like the width of the tape part of the tape is nothing compared to the radius of the roll of tape, right? Like the empty space in the middle is most of it. So it's probably changing like 5%. And so what this is going to do is it's going to make your fonts 5% too thin or 5% too fast at the extremes. You're not going to notice unless you're writing like Moby Dick on a strip of masking tape, which would be an awesome art project. So if you do that,
if you solve that problem, let us know.
Use a capstan drive and then send us the links because that's an awesome hack. I used to wonder when I was a kid, actually, I remember trying to solve this sometime, must have been in high school because I knew about calculus at the time, trying to solve out how the tape, like a cassette tape, would know what speed to turn at because the tape has to be moving through at a different speed because the radius of the, spool of tape is constantly changing. And I was trying to do that math to figure that out. And then, of course, the answer is it's got a capstan drive, which just pushes the tape through at a completely linear speed. And the take-up reels are just on a little bit of tension and they spin faster or slower, however much they need to. So I did like all this math. It must have taken me like a whole afternoon of hard brain-numbing thought to get this figured out. And then I opened up a tape recorder and figured out how it actually was done.
Oh, well.
Yeah. Boy, and speaking of theory and practice, Wyman's Workshop had a video about a year ago now, and we wrote it up, Theory, Practice, and Ducted Fans. And this is actually the second part of a two-part video series. The first is him kind of building this large-scale ducted fan made with a Harbor Freight bench grinder motor, and it's kind of 40 centimeters, 1.5 feet in diameter, something like that. It's a pretty big 3D printed ducted fan. Anyway, this is the video where he starts going through the specs and trying to like figure out what he did right and what he did wrong and play around with different fan designs. I just love this one because it's a very low-key video, but it's also got him doing kind of, real science on the thing. He wants to calculate how much thrust it's putting out, and one of the things he does is he puts a piece of fishing line through the nose cone and then attaches that through a lever system to a scale so that he can figure out how much thrust the thing is pulling on the fishing line. And you could tell he's doing it right because along the way he notices that like the 3D printed pulley that he has the fishing line go over actually has too much friction and it's messing up his measurements. So he like replaces that with a bearing, and then the motor like pulls a lot more smoothly on the weight on the scale. But like he also notices that there's different flow speeds when he has his anemometer trying to figure out how much air this thing's pushing. He notices that there's different air speeds in different regions of the output of this thing. It's this kind of careful observation and like attention to the little details that really makes kind of, a working scientific experiment different from a failed scientific experiment. But the fail is yet to come. He also builds up kind of a theoretical model of how a ducted fan should work. And that is, he kind of imagines a donut-shaped what is it? It's a cylinder of air that goes through the body of the ducted fan, and then he cuts out the center cylinder, which is like the nose cone and spindle of the motor. So he's kind of imagining the volume of the blades as they push air through there. And he does his math on this, and he determines that he should get so much force out of it. And when he finds out that he gets a lot less, he has to scratch his head and figure out why. Turns out he's way overloading the motor, so he starts building some other fan blades with fewer blades so that they don't overgear this poor motor. And he gets that into ballpark, but then he gets results that are better than his theory predicts. He redoes his thinking that instead of taking out the nose cone volume, he just needs to leave it in. That actually makes more sense because where would that air be going if not through the fan? And there's some other refinements he has with, a bigger volume on the outside than pushed through and stuff. He eventually tweaks his physics model, but the video has this really nice kind of interplay between him not getting enough performance and then getting too much performance. And that really means that he's got his physics model wrong. So he tweaks his physics model and he kind of goes back and forth until he gets them to agree across a wide range of different configurations and fan pitches and different numbers of blades and stuff like that. The trick with ducted fans is you want to get better performance than you would by having the fan blade rotating out in the open. By putting the shroud around it, you can kind of force more air into and through it, and you lose these tip eddies and tip vortices and stuff like this. Anyway, aerodynamics stuff, you should get kind of 15% more efficiency out of it. And he does do that in the end. So it's lovely that he kind of verifies that this all works and simultaneously gets his math right to match what's actually happening in reality. And the funniest thing is it ends with him saying he's going to experiment with more different inlet shapes because that makes a big difference about how much volume of air it can push through it. And he's like, we'll save that for next time. And the video's a year old. So don't hold your breath.
The thing that gets me about these kind of projects is they're the kinds of projects that would never have been possible without additive manufacturing. You couldn't, well, I mean, I guess you could iterate quickly enough.
Cut these blades out of wood.
Cut them out of what? Yeah, cut them out of wood or foam or mold them out of plastic or something. All of that stuff would just take so much time and so much effort that things like this just wouldn't ever be done by the sort of the hobbyist level person. I'm sure Pratt and Whitney or General Electric engineers from the 40s and 50s would probably be laughing at us compared to, what they managed to do, but they also did it with essentially unlimited budgets
Yeah.
and workshops and machinists and skilled trades and all that working with them. But to be able to do this on your desktop, crank out new parts when you need them to, a little bit here, a little bit there, just, A/B testing, that kind of thing. Hugely, hugely powerful. Although I seem to remember the duct for this actually was made out of wood, wasn't it?
Yeah.
At least one version of it.
If you like woodworking stuff, the previous video is all about how he made it. And he like takes a bunch of wood veneer and like curves it into the right shape and glues it there. And, he like custom makes this whole shroud. It's really, it's nice, but it's carpentry.
A lot of machinists make fun of working with the cellulose foams, the carbohydrate foams, but the dead tree carcasses and all that. But it's a heck of a material. It can do a lot. It's easy to work with, and it's kind of abundant. It even grows on trees. And my last pick is a retrotectacular piece, How Television Worked in the 1950s by Jenny List. I have to admit that retrotectacular was one of the first things that attracted me to Hackaday back when I was a reader. I lived for it seemed like they always came out on Wednesdays, and they almost always seemed to be written by Christina. And I think you told me once it doesn't count as retrotectacular unless it's black and white, and unless it's got a ready kilowatt.
Ready kilowatt test.
Some schlocky old logo or corporate thing or something like that. And this one kind of has that. It's a very, very, I'm not going to say dumbed down look at TV, but it was written for the general public, and it was very simplified version of how TV works in 1952. So this is pretty early in the whole TV revolution thing. I mean, it's the early part of the 50s. Things were only just really starting to get going with television penetrating into the market. And people maybe wanted to know how this thing worked, maybe not, but this film answered the question.
Told them anyway.
It told them whether you wanted it or not. It's necessarily got some animations in there and talks about how, a spot of light hits the image orthicon and is translated into an electric charge and all this stuff. And it's all correct, but like I said, it's kind of simplified. And it does get a little bit more complicated further on when they talk about synchronization and how the signals were actually transmitted. So it's a good little film. It's a nice little trip down memory lane. But the thing that I got out of this was the fact that TV used to be a shared experience. And Jenny touches on this in the article too. But it was very much a shared experience. In the 1950s, maybe it was the Honeymooners or whatever, Western was on or what have you. In the 80s and 90s, it was, what was it? It was, Seinfeld. And you would, all watch Seinfeld on whatever night Seinfeld was on. And you would, stand around the next day talking about it. Everybody watched it at the same time. Everybody talked about it the next day. So it was this kind of shared experience. But it was also a shared experience in another way, in a very engineering and technical way. And this never really struck me until recently. Everybody was watching an electron beam zip back and forth across the inside of a tube and lighting up phosphors. And the electron beam was in the exact same place on everybody's screen at the exact same time. And that was the exact same time that the electron beam was scanning back and forth in an image orthicon somewhere in a TV studio. And it all had to be in sync, or else it didn't work. Not only do you have the shared experience, the shared social experience of watching The Honeymooners or I Love Lucy or whatever, but you also have this shared technical experience that everybody's TV is doing the exact same thing at the exact same time.
This video here was made to kind of explain at a reasonably accurate level how a cathode ray tube television worked back in the day. And, it's got all the parts that matter, right? It's got the coils deflecting this electron beam around and everything. It does explain it at a very low level. And I think that's kind of interesting from a historical perspective as well, because this was explaining a, new magical device to people and showing them how it worked in the time that it was the new magical device. It's kind of a neat time capsule in a way.
Yeah.
But it does kind of, capture this 1950s, here's how the technology around your world works vibe.
I think that was part of the marketing too. They felt like, we need to explain this to the people. before
Otherwise,
they really
they'll
buy
be
into
scared
it.
of it. Yeah.
And I don't know if that was necessarily necessary, but much like people don't need to know how smartphones work to gobble them up, in their millions and billions, they just want their goodies. And I think this was very much we need to sit down. Everybody's talking about I Love Lucy. We gotta see what this I Love Lucy thing is all about.
Images picked up by cameras and turned into radio wave signals which tell a fleeting invisible beam how to paint moving pictures in your home. Let this be only the beginning of your study of television.
My first quick hack this week is exporting data from old gear through LCD sniffing. This is a hack by Ure Spiller. The problem here is an old device, I think it's a spectrophotometer, that doesn't have any kind of modern interfaces. How can you get the data out? The answer is by putting your probes on the wires that lead to the LCD screen and decoding them. This is a technique that basically always works whenever you can get access to the LCD screen on an old device. We've seen it a number of times on a range of devices. This is your reminder that that's a great way to get stuff out of old machines when you don't want to point a camera and use computer vision on it. Next up, Paul Price, B-Motion combines ESP32 with PIR sensor and USB-C. And boy, that basically sums it up. This is a sweet little custom board that Paul made, and it's just got an ESP32 and a PIR sensor on it. But that combination is exactly what you need if you want to do an occupancy sensor or any of the kind of triggers for automation tasks you might want to have in your smart home. ESP32, of course, has a low power draw when it's sleeping. PIR sensors have a ridiculously low power draw. So this thing can run on batteries for probably a year or so if it's not triggering all the time. There's not much to this project. It's really sweet, but it's probably exactly what you need, and maybe 10 of them scattered around your house. And last up, Flexures make this 6DOF positioner accurate to the micron level. This is a research project by Jonathan Hopkins, who ironically is at UCLA. It's a sweet 6 degree of freedom positioner called Hexablade, and that's because it's made up of 6 blade-shaped flexures. Each one can only move in its one axis, and combined they make a completely free platform. It doesn't move much, but it moves reliably. It's driven by voice coils, so it should last for a good long time, and it's fast and accurate. Really sweet design, and it was kind of a new flexure design for me, so go give it a look.
Okay, my first quick pick is Reimagining the Resistor Color Code Cheat Sheet. This one is by Andrew Jetalo, and it kind of turns the concept of the resistor color code on its head a little bit. I'm not sure this fits everybody's brain, but apparently it fits Andrew's, because he wants to think of a color code for resistors. For example, a 560 kilo ohm resistor. He wants to think of that as 5.6 times 100,000 ohms, instead of the traditional rendering of the color code makes you think a bit more like 56 times 10,000 ohms. I'm not sure the advantage is going to work for everybody. It doesn't really work for me, but it's a nice new reimagining of it. And really, anytime you are presented with something that is canon, it really kind of deserves to be looked at again. The only thing I'm not sure about here is he going to do something about the naughty sort of mnemonic that we use to remember the sequence of the color codes? It needs a little bit of reworking for this day and age, I think. Next up, Altoids 8800 puts a front panel in your pocket. This one is basically an Altair 8800 computer stuck into an Altoids tin. It's got all of the stuff that, maybe not exactly all of it, but a lot of the stuff that was on the iconic front panel of the Altair 8800 computer back at the very beginning of the computer revolution, when you had switches and blinking lights and you had to enter the program in manually. That has been condensed down into a form factor that'll fit into an Altoid tin. And it's not an emulation. It's the actual thing. It's an Intel 8080 computer with all the supporting chips. Makes me wonder why the Altair had to be so big in the first place. Why couldn't we make it this small back then? And I think the answer is the power supply, which was massive in those things.
That's what I was thinking too.
Yeah,
It's the giant switches and the power supply. That's the only explanation. Oh, and the size of the lights back then. They all had to be incandescent lights, maybe? I don't know.
Yeah.
I was wondering exactly
LEDs
the
were
same
hard to
thing.
come from. Yeah. This is why we can't have small things.
Yeah. They didn't have Altoid tins back then.
And finally, 3D print finishing by spraying glazing putty. This is Darkwing Dad taking a standard PLA print with the usual sort of print line artifacts and little nubby things that you don't necessarily want to have. His secret that he discovered is taking glazing putty. Now, this isn't the stuff you get a little tub of and you use to paint a window. That's glazier's putty. This is glazing putty as in Bondo, basically. So it's a squeezy tube full of this polymer mix. Mix it with a little acetone, thin it down, put it into a spray gun. He uses a little airbrush like airbrush artists would use, and spray that on. The acetone evaporates very quickly, leaves behind this sort of high solids compound that can flow into layer lines, fill in gaps, and a couple of coats of that, sand it down, build it up with some high build primer, and it really does the job. These prints of his were coming out super smooth and almost looked like they were vacuum formed rather than 3D printed. Nice little tip to keep in mind.
All right, that brings us to the Can't Miss articles. These are long-form original pieces written by our fantastic Hackaday staff. And I'd like to pick Matthew Carlson's How a Smartphone is Made in 8 Easy Blocks. And if you don't know what's inside the little black box, you should definitely give this a read. It's kind of a bit of a bird's eye view. It's kind of just the block diagram of what's inside the phone and which parts do which. But even so, there's still some interesting tidbits for you here, like kind of conceptually the application processor, the CPU and its associated things, is really separate, at least in older phones, from the radio side stuff, the baseband processor. And so these two kind of talk to each other, although in more modern phones, they kind of also have some shared memory and are able to trade commands with each other in a way that they didn't 10 years ago. Similarly, the SIM card plays a more active role in this kind of multi-processor world inside the phone. It's kind of fun to read about how it's not just a memory, it's also got a little microprocessor in there and can run commands given orders from the application processor. And then he talked about sensors, displays, cameras. His example of how the design for modern cell phone camera lenses is made or completely upends the kind of old school, it looks like a lens design, is really interesting. And I think I'm going to be able to convince him into doing a standalone piece on smartphone camera lenses because the tech there is phenomenal. Anyway, if you're interested in just kind of taking a first glimpse into the stuff that's inside your phone and, maybe learning what the right keywords are to do the search about the stuff you care about more, this is actually a really cool article. And I think, in the same way that movie from the 50s about this is how a television works is informative and useful, I think this one is the same thing, but for the magical and inscrutable device that we all have in our pocket.
The diagram of the lens just sort of, I guess it's an iPhone 7. That just sort of broke my brain. I had no idea. I mean, everybody talks about, this phone has this great camera and oh boy, wow, this camera. And I really thought that had mostly to do with the sensor itself.
Yeah.
And it turns out maybe not so much. What you put in front of the sensor, as with film cameras, what you put on that body of that camera was far more important than than the camera itself and the film you use and all that. And the fact that you're able to squeeze these bizarre funhouse mirror-looking optics into such a small space and make it all work, the optical engineering alone is just mind-shattering. It kind of reminds me that optical engineering is a thing, and it's not something we talk
right.
about a lot, although we have talked about it with Joran Vlegar, who does Huygens Optics on YouTube, and he recently did an all-in-one monolithic Cassegrain reflector telescope out of one solid block of glass. And he touched on a lot of this aspherical stuff, that there's very small variations that have to be built into a reflector or a lens to make up for these chromatic aberrations and all these other problems that a real world lens suffers from. And to be able to do all that in one package like this that fits into something that's so slim and so space constrained it just blows my mind. The thing that really gets you is the header for the last section here in the article. Put it all together and throw it away. and that's, all the effort that goes into making these things, it just disappears in a couple of years when the phone is obsolete and you're not using it anymore and you've gone and lined up and got your new one.
If you've ever opened up a cell phone and looked at all the component parts, or maybe swapped some of them out because something was broken, this article will be familiar to you. So it may not, it may not be groundbreaking if you're already a cell phone nerd, but if you aren't a cell phone nerd, you definitely should give it a read. It gives you kind of a good overview of the lay of the land.
My pick for can't miss article is Will We Ever Shake the Polaroid Picture by Christina Panos. I have a soft spot for Polaroid. I can remember, and the genesis of this article is the fact that they were able to engineer the camera, engineer the film. They had to have the chemical engineering to make the film process workable in the instant format. They had to engineer a film pack that could be, put into the camera, handled without exposing anything. They had to put a battery inside the film pack. That's what really blew my mind at the time, because in my world, batteries were these big hefty things, D cell, C cell, whatever, 9-volt batteries were these big chunky hefty things. They weren't flat. Now all of a sudden we had flat batteries, Pola Pulse batteries. I mean, it's trivial these days. My phone's got a basically flat battery in it. Your phone does too. But that was revolutionary at the time, the Pola Pulse battery. And getting those things from old used up film packs was always a treat. There wasn't much left of them as far as charge goes, but they were great to pull out and experiment with. Anyways, the article goes into a lot of detail about the SX70 camera, how it was developed, what it was. If you're not familiar with it, the article will give you a good basis in that, and the fact that it was chock full of 300 transistors, which was a sizable number for the day. The thing that really gets me about the article is that Christina really focuses on the tangibility of what an instant photo is. It's trivial to make a photograph now. Stick your phone at something, put your thumb on the button, boom, you've got it. It's instant. It's more instant than an instant photo from an SX70 ever was, because it's right there, right now. You don't have to wait 30 seconds or a minute or whatever it was to get the chemistry to give you the image. Having an instant photograph now, there's no cachet to that. Back then, there was a huge cachet to that. But you also now don't have anything tangible unless you take that and send it someplace, get it printed up nice. You had no choice with the instant camera but to have a tangible object, because that piece of film was your negative, it was your print, it was your chemistry lab, and it was recently attached to a pack that had a battery in it. It's got this whole physicality to it that a photograph made today on a phone doesn't have and will never have. And I think that's kind of something that's missing. It's a thing that was important at the time, and I think that's why, as Christina says, there's kind of a revival of the SX70 and other instant formats, because people want to be able to have a token of what just happened. And I think it's a good point that she makes, is that a lot of the physicality of photography is missing today, and you can kind of bring it back a little bit with the instant process cameras.
Dude, the chemistry that goes on in these old Polaroid things. My parents had I guess even at the time, it was a relic Polaroid camera that used some even older film. It was a black and white Polaroid film. You had to pull the picture through a little roller thing that would then like essentially squeegee chemistry onto it.
Yep.
And then it also had a second one that you had to coat it with at the end that came in a little tube. It was a fixer and a glossy cover at the same time for the photochemistry. And so you'd have to pull it through this one, let it dry a little bit, and then you'd put this like fixer/gloss thing on there, and then you'd have to let it dry again. And then came along, the kind of canonical Polaroid film, the one you think of here, the one that's got that, it's like a square inside a rectangle. Again, the reason it's a rectangle is that they had a dose of the development chemistry in that little fat tab. And inside the camera, there's a squeegee again that like presses that out across the film part to develop it inside. Like just the technology of packing all of the chemistry live into these little packages and then, having it essentially run all the darkroom chemistry for you more or less reliably on the fly like that is really, I mean, it's kind of stunning now that I look back on it. I took it for granted when I was a kid, of course. But then you get this whole, like, I remember in the mid 80s, and Christina puts up this cover of a Peter Gabriel album where it was manipulated. There was this whole like thing with people like smudging them intentionally and stuff, because while it's developing, these chemicals are all still wet. You can kind of push them around with your hand and do kind of funny things on it. And even in one of these pictures she has, it's got like bands across it, and that's from pulling it out at an inconsistent rate out of the thing. If you pull like fast, slow, when you're spreading the chemistry across it, it'll like do it unevenly and you can get bands and stuff. I don't know, because it was a physical process, because it was a real physical chemical process, it kind of afforded all of these extra funny ways to manipulate it that, you could do just with your thumbs if you do it quick enough before the reaction takes place, right? You can't do the massaging around necessarily in the same physical way as you could, but man, someone could write an app for that in 10 seconds, and you could do exactly the same thing that you could do with Polaroids back in the day. I wonder if that exists already, or if I'm going to be a millionaire by writing this myself.
Maybe, huh?
That about wraps it up for this week's Hackaday podcast. If you see anything cool or do anything cool, you can write to us, tips@hackaday.com. If you've got comments on the show, write to us, editor@hackaday.com. As always, the links will be found at hackaday.com/podcast. And until next week,
keep on hacking. Hack on keeping. Boom.
Boom. Put it in the can.
Nice.
At this point, I'll run some music.
Doodly doodly doo. Okay.
Bazazaba.
Sure will. Well, wait a second. What the hell was that?
I'll handle that in post. Yeah. I was like, yikes. Excuse me.
Okay.